Hi, in this video we will find the derivative of inverse trigonometric functions using implicit differentiation. Well, let us start with sine inverse. Y is equal to sine inverse of x, and we want to find what is dy dx. By definition, we know that this means that sine of y is equal to x. Well, we have to be careful. Y needs to be on the interval pi over 2 and negative pi over 2. Yes, and the goal is, as I mentioned, find y prime or dy dx as a function of x. Yes, because the y is equal a function of x. And then, okay, so we will use this version here and consider it as a function, as an equation in x and y, and start differentiating. Implicit differentiation. Differentiate both sides with respect to x. Here, this is 1. On the other side, we use the chain rule. This is equal to that. Well, we found it. Y prime is equal to 1 over cosine y. Very nice. This was what we were looking for. Well, not really. We are looking for y prime as a function of x, not function of y. Well, that means what? That means that we have to turn 1 over cosine y and write it in terms of x. You see, this equation here says that wherever you see sine y, you can write x for that. And this, we have cosine y. There's a good relation between cosine y and sine y. Remember that identity. And this tells me that cosine y is square root of 1 minus sine squared of y. Well, it can be positive or negative of that, okay? But if y is on the interval pi over 2, bigger than negative pi over 2 and less than pi over 2, we know that cosine of y will be positive. Remember the graph, it will go like that. It is positive. So that means that cosine of y in that interval is 1 minus sine squared of y. And well, that gives us everything that we want. We can write this and then root 1 minus sine of y is x squared. Yes. This gives us the first rule, the first differentiation rule that we have. And this is 1. This guy. And this is the rule you have to keep in mind. Derivative of sine inverse is equal to 1 over root 1 minus x squared. You see, the technique is very nice. There are two things. One is using implicit differentiation, and then at the end writing back everything in terms of x. These are two important things that we know. Well, let's do one more. I will do this time tan inverse. Okay, not this one. Y is equal to tan inverse of x. We know this means that x is equal to tan y. And well, for what values of y? Values between negative pi over 2 and pi over 2, not including the endpoints. Okay, very nice. Here now we have an equation in x and y, and I can differentiate both sides with respect to x. And well, I know what is derivative of tan y in terms of derivative of tan y. It is secant squared of y. We are using the chain rule here. But remember, secant squared y is always equal to 1 plus tan squared y. This means that we have a version that already has everything written in terms of tan y. Why do I need that? Because when I write y prime, just solving this equation up there, I get 1 over tan squared of y. And okay, now I can use this identity, well, this equality, and replace tan y by x. Okay? And this is the second rule that we prove here, that derivative of arctan or tan inverse is 1 over 1 plus x squared. That was the second rule that we proved. The other ones are exactly same way. You just need to do a little bit of changing at the end, changing y to x as we did in these last steps. But the technique, the trick is the same thing. So let me just write the derivatives of inverse trig functions. Let us start listing all of them by sine inverse or arc sine. This is 1 over 1 minus x squared. The derivative of cosine inverse of x, this is negative 1 over 1 minus x squared. And the third one is the tan inverse or arctan. These are the ones we found. This is 1 over 1 plus x squared. Now the 1 over version of these guys, so d dx of cosecant inverse of x, this is negative 1 over x times x squared minus 1. Fifth one is d dx of secant inverse. This is 1 over x squared minus 1. And the sixth one is d dx of cotan inverse of x, which is 1 over negative 1 over 1 plus x squared. Well, you have to know the chain rule version of these ones. When you have u here inside, you will have u prime up there for all of them. U prime up there, well, and so on. So the chain rule version of all of them will work in a nice way. Okay. Then let's finish video with some examples. Okay. Find the derivatives of these functions. Okay. Let's see. This one is black. Derivative of f. This is a product rule. Derivative of first one times second one plus the first one itself times the derivative of the second one. And this gives e to the power x. The derivative is e to the power x. And e to the power x times derivative of sine inverse is 1 over, so multiply to e to the power x with e to the power x over 1 square root of 1 minus x squared. How about this one? G prime of x. This is, you see, u to the power 3 here. So we have the general power rule. It will be n3 times u prime times u to the power 1 less. And this gives us a derivative of a secant inverse is 1 over, so that 3 comes from here, 1 over x root x squared minus 1 times secant inverse x to the power 2. And this guy here, well, h prime arctan or tan inverse of something. So h prime of t, wait a minute, this needs to be x here. Yes, so we have h prime of x is, h prime of x is, you see, derivative of tan inverse is 1 over 1 plus x squared. Yes, now we have a function up there, so it will be that you apply the chain rule, 1 minus x over 1 plus x prime over 1 minus x 1 plus x squared, 1 plus that is squared. Well, what we have above there, you have to use the quotient rule here. This will give us negative 2. You can do it easily. You just need to simplify a little bit. And down here we have 1 plus 1 minus x squared over 1 plus x squared. You find the common denominator, you simplify. I'll just write what we have here. Negative 2 over 1 plus x squared over 1 2x squared plus 2 over 1 plus x squared. And oops, this way. This cancels with that. The final result is negative 2 over 2x squared plus 2, which you can simplify a bit more. You get negative 1 over x squared plus 1. Well, these were the examples we had here. So you have to learn these new rules, and you see that how this rules, we obtain these rules by applying the implicit differentiation.